is the lesson for Chapter 7, Section 7, titled Exponential Growth and Decay, and I'm going to break this into two different days, and we're going to look at growth and decay factors first. And so exponential growth is when we end up having this situation where we have an output here, and that output is set equal to an initial amount and then multiplied by a growth factor. Now I know it's a growth factor whenever this growth factor, is larger than 1. Because when it's larger than 1, what we found out is when we used or graphed an exponential function, we went ahead and saw a graph went uphill from left to right. And it makes sense because my outputs are gaining. They're growing as my x values. My inputs are gaining as well. And so when it's decay, though, we see that the growth factor is actually a decay factor because it's decreasing. And you can see that in the graph. Whenever b is between 0 and 1, so when it's a fraction, that means that our growth factor, or our decay factor in that case, is actually decreasing. The y values are decreasing as my x values here are getting bigger, as you can see as I run along that graph. And we're going to see those situations in these problems. And so let's take a look at our first one that we'll end up seeing. And it says that the town manager reports that revenue for a given year is 2.5 million. The budget director predicts that the revenue will increase. Okay, so increase tells us that we have a growth factor. And so I know when it's a growth factor, that means we have growth rather than decaying. We're getting bigger rather than getting smaller. And it's an increase of 4% per year. And so what that means is at the end of 1 year, it's 4%, but then you got to add on that extra amount that was increased and then calculate that again the following year. So if the director's prediction holds true, how much revenue will the town have available after 10 years? And then we're also supposed to write an expression to represent the monthly increase in revenue. So let's start with our equation. So our growth equation looks like this: a times by, and then b to the x power, where a is the initial amount. Well, right here, this is the initial amount. 2.5 million. This is your a value. Now, I know it's in millions, so I'm just going to write down 2.5. And I know this is going to end up being in millions. And so maybe I'll write that down, in millions. And so I've got y equals 2.5. That was the initial amount. And then times by our growth factor. Now, our growth factor, well, if I multiply by 1, it doesn't change the value. But it's increasing by 4%. Well, 4% is the same thing as 0.04. And so what I'm going to do is I'm going to take that 0.04, since it's increasing means an addition sign, by that amount, by that 0.04. So that makes 1.04. And so that's what I'm going to call my growth factor, 1.04. The initial amount, so 1 times a number doesn't change the value, but it's growing by 0.04. And so that's why I use that as my growth factor. And so then I'm going to take that value and I'm raising it to a power. Well, the power is the number of years. Number of years in this case, because that's what the problem is talking about. So they said 10 years. And so that's what I'm going to end up using. And so now I've got some work. So in the calculator, now this is definitely a calculator problem, you're going to input 2.5 times by, and then actually I'm going to go ahead and do into 2 steps. I'm going to start with the 1.04, and I'm going to bring that to the 10th power. And so when I did that on the calculator, this is what I ended up getting. I got 1.4802, and then it kept on going. It was actually 44285 is what my calculator showed. So I'm going to use that number, and I'm going to multiply that by 2.5 million. I'm just going to do by 2.5 for now. So times by 2.5. And when I do that, this is what I got, 3.7006, and so on. And then it keeps on going. And this is in millions. And so I'm going to just round this off because this is just a prediction now. I'm going to just call this 3.7 million. And that should be the prediction of how much revenue. So 3.7 million dollars in revenue. And so what I'm going to do next, though, is now we're going to take this equation. We're going to find out, well, how does this work if we want an equivalent monthly increase. So let's take a look at what we've got. We've got this 1.04, and that was that's our growth factor. But this is in years. And so what we want to do is we want to convert to months. And so what we see is this is our initial amount here, what we had before, and X was the number of years, and we just put in 10 there. Well, we want to know months, and so what we're going to do is we're going to use that same growth factor, but we're going to use a little algebra trick. You see, months, there are 12 months in a year. So what I did is I saw that, well, okay, I have the same exact value. These are equal to one another. See, 12 over 12, this part right here, this equals 1. And so I haven't changed the value at all. And so what I'm going to do is I'm going to use another algebra trick that says, okay, well, if I have this, I could go ahead and modify it a little bit. I could rewrite this as a power of a power. And so I'm going to write this as 1/12, and I'm going to put the 12x on the outside. And so now what I can do is I can find out what the monthly growth is. So this is going to be monthly growth factor. So I need to put in growth there. We'll say growth factor. And so now I can go ahead and figure out what that's going to be. So I can put that in the calculator. So I'm going to write in the calculator. And this is where it's nice to have the fraction button. So 1.04, and then I'm going to press the exponent button, and I'm going to enter the fraction of 1/12. So 1 over 12. And then I got this number here. So I get now a 1.003, and it continues on. There's a 2.7, and so it continues on. So I'm just going to round that off to 1.003. And then I've got what's left over. Well, I've taken this part right here, but I still have that 12x. And so now I'm going to go ahead and multiply that. So that is our growth factor. So now what they can do is they might say instead of 12x, we could just write the number of months now. And so since we've changed this to months, we could just write 1.003m. And m stands for, instead of years, now we are in months. And so now if you enter the number of months, that would give you that value. You still use your initial amount, but now instead of the growth factor of 1.04, you'd use 1.003, enter the number of months, and that would give you your answer. So let's move on to the next one. It says a wildlife manager determines that there is approximately 200 deer in a certain park. Okay, so this right here is the initial amount. So that's the initial. And so then it says the population is growing. Okay, growing, that means it's getting bigger at a rate of 7% per year. How many deer in the park after 4 years? All right, we're going to use our equation. Y equals A times by B to the x power. I know the initial amount, that's 200 deer. And the growth factor, well, the growth factor is 1 plus 0.07. So you just take that 7%, change that to a decimal, and add it on to 1, and that's how much it's growing by each year. So 200 times 1 makes 200. That's the initial amount. And then 200 times 0.07 is the growth after that first year. But we have after 4 years. And so what we're going to do is we're going to bring this amount right here to the 4th power. So we can go ahead and enter into the calculator. So I'll enter 1.07 to the 4th power, and that gives me this number. I've got 1.31079.601. So that's the number my calculator gave me. I can go ahead and use that number and multiply by 200 now. So times by 200, and it gives me this. It gives me 262.159, and so on. And so we can't have 0.159 of a deer, so we're just going to say about 262 deer is going to be in the park after the 4 years. And then it says, well, if the carrying capacity for the park is 350, how long will it take before the deer population reach the carrying capacity? Well, there is a way later on in Algebra 2 that we'll be able to solve this directly. But right now what we have to do is kind of a guess and check method. So we'll see that logarithms allow us to solve for the exponent, because that's what they're asking for. See, now we know what the y value is. We know y, and actually let me go ahead and rewrite the formula there. So remember, the formula goes y equals a times bx. Well, we know what y is. Y is 350. We want to find out, when is it going to be 350? We know what a is also. A is the initial amount of 200 deer. And we know B. B is the growth factor, 0.07. We just don't know X. There's a way later on, again, to solve for X, but right now we're just going to do some guessing and checking. I know, well, 262 was 4 years, and we got to get all the way up to 350, so I might try doubling that. Let's try 8. So this is just a guess and check. So we're going to guess 8 years. And so let's see where that gets us. And so I go ahead and substitute in 200 times by 1.07 to the 8th power. So I'll do 1.07 to the 8th power, and then times by 200. And that gives me a value of, again, I want something close to 350, and it's pretty close, 343.6. And so now let's try 9 years. Okay, so 9 years. See where that puts us. Really close. Let's see if it works out. So 200 was the initial amount, times by 1.07 to the 9th power this time. And so we'll enter in the calculator 1.07 times by, or actually to the 9th power, and then times by 200. And that gives me 367. So this is going to be what Y is, which is the number of deer, and that makes 367. So we see that it's in between, so between 8 and 9 years would be our answer for this problem. So let's take a look at another problem. And here it says state whether the equation represents exponential growth or exponential decay, or neither. And so remember, growth is going to end up being this. So we saw on that first page I showed you, A times B to the x power is our exponential formula, so B would be greater than 1. That's going to be growth. Where decay is going to be A times B to the x power, but B is going to be between 0 and 1. And so that's what we're going to see. So that means it's a fraction. It's a fraction of a number. And so that's what we're looking for. But anytime it's exponential, we're going to have x as the exponent. And that's what we see here. So you're looking at the growth factor or the exponential factor. And right here, the 3 is what I'm looking for. So we'll say that B is equal to 3, which is greater than 1. So this is growth. So this is exponential. Just write EXP for exponential growth. Where here, our factor is a decay factor, and the reason is that B equals 0.3, which is less than 1. So that means that it's exponential decay. It's getting smaller. This is not an exponential function. You see the exponent is known. It's known here. It's equal to 2, so this is actually a quadratic. You didn't need to know that or tell me that, but this is not a exponential function. This is exponential, and I see that the growth factor, or the factor, not a growth factor this time, the B value is 0.9, and that is less than 1, so this is also decay. This is exponential decay in this case. So on this problem here, it says a business purchases a computer system for $3,000. The value of the system decreases. Okay, so this is a decay problem. That means it's getting smaller. Decreases at a rate of 15%. And so remember, 100% is what it was initially. That's what it was. It was $3,000. $3,000 is 100%, but it's decreasing by 15%. So what we have to do is we have to subtract that 15% from the 100%, and that leaves us with 85%. And that's the number that we're going to multiply the 3,000 by. After the first year, you multiply 85% times by 3,000. That's going to give you the value of the computer. But we want to know after 4 years. So we're going to use our exponential formula, which goes A times by B to the x power. And so we're going to start with the initial value. The initial value is $3,000. And so 3,000 times by the decay factor, which is 0.85 to the 4th power. And so again, 0.85, because you subtract, because it's decreasing, so decreasing means minus, subtract the 15% from the 100%. So we've got some calculator work to do. We have to do 0.85 to the, and then it's to the 4th power. And that gives us, is what I got 0.522000625. That's what my calculator says. And then multiply that by 3,000. And so I times by 3,000. And that equals, and then I get 100, or actually, I'm sorry, $1,566. And it looks like 2 cents. 2 cents because I had the 0.01 but then an 8. So I'm going to just round that to $1,566.02. That is the value of the computer after 4 years. So that's what we'll end up seeing on the assignment tonight. Good luck.